Welcome back. We had just done 7 and 8. I want to jump in to do number 9 here. Now for number 9, you're asked to expand the logarithms. Remember our expansion and contraction tools for logarithms? They were, if we had a log any base of a product, we could take the sum, the same base, of those logs. So log base b of u plus log base b of v. If they were divided, we could do the same thing, u over v. Notice it is the log of a quotient. This isn't log divided by, not the log of u divided by the log of w. This is the log of that quotient. Turns into the subtraction. Again, the bases must match. The numerator first subtracted by the denominator. And we often associate denominators with negative exponents. So the fact that it turned into a negative log should be reasonable. Don't confuse this with the change of base formula, the whole log of u over log of b. Don't mess this up with the change of base formula. They're very different arguments. Change of base has the log on top and a different log on the bottom. This is the log of that quotient. Be very careful about that. We also know that the log base b of u to the n, something raised to a power, is equal to n times that log with its base of u. And I've mentioned this on the other, on Chapter 5's review, and you've certainly read in the section, all of these actually come from our a to the m times a to the n logic. If you're multiplying two things with exponents, what do? Well, you add the exponents. This is saying the same thing. Logs are about exponents, so this is asking, what happens to the exponent when we multiply? Well, you add the exponents. What happens to the exponents when we multiply? We add the exponents, as long as the bases match. It's the same exact argument in exponential form, in logarithmic form. Similarly, what happens to the exponents when you divide? Well, you subtract the exponents to the n, sorry. You subtract the exponents when you divide. This asks the same thing. What happens to the exponents when you divide? Well, you subtract the exponents. Logs talk about the exponents. This last one, what happens to the exponents when you raise something to a power? Well, you multiply the exponents. What happens to the exponents when we raise something to a power? Well, we take that power and multiply it by the old exponent. The logarithm expresses the exponent. Real quick theory with those, but these are very powerful tools. So number 9 says that we've got the natural log of the square root of x plus 1 over x plus 2 squared. So of these, this is primarily the log of a quotient, the log of two things being divided. So we can turn that into the log. This log just happens to be the natural log, so the natural log of the square root of x minus 1, plus 1, minus the natural log of x plus 2 quantity squared. Okay, so we look to see if we can simplify it any more. This first one is the natural log of x plus 1 to the 1/2. Remember, radicals are 1/2 power. And we have a tool that says if you're taking the log of something raised to a power, that power can come down as a multiple. So that 1/2 is going to come down, 1/2 natural log of x plus 1. Now be careful. You might think that you can just kind of distribute, sort of, and say the natural log of x plus the natural log of 1. But that's not what this rule says. This rule says we can split them up under addition if they started as a multiplication. This is not x times 1, this is x plus 1. This is not the same as this. We can't use this tool. That's done. This 2, on the other hand, is a power just like this is. So that power can come down. So 2 natural log of x plus 2. And again, that x plus 2 might look tempting to do something with, but we can use our expansion tools on a product, a quotient, or a power, not a sum. So that problem is done. This tool of expanding was not terribly helpful for us in this course, The contracting tool that we're about to do was more helpful. But for those of you going on to calculus or chemistry or certain sociological or business applications, this expanding tool can be extremely helpful in simplifying a problem. It takes a complex interaction here, the square root, the logarithm, the power, the division. It takes the complex interaction and makes it into a list of smaller, nicer interactions. I mean, who wouldn't rather multiply by 1/2 than deal with a square root? So this tool is used a lot later on when you get to more sophisticated operations. So keep an eye out for that. 10 asks us to use our contraction tools to write this as a single logarithm. Trying to find a pen that's going to work. Well, let's see. So now we're trying to go the other way. We have an expression that's in pieces. We're trying to bring it together. So the first thing we might notice is that we have this multiplier out in front. We'd like to be able to use the addition tool to bring it together, but our addition tool says we have to have a logarithm plus another logarithm. This 1/2, what to do with this constant? There's no constant here, so we can't use this tool yet. How do we deal with the constant? Well, our power property down here, what it's called, product property, quotient property, and power property, says if there's a constant out in front, multiple out in front, we can bring it up as a power. So what do we do with that 1/2? Well, we can bring that 1/2 up as a power. And I'm going to rewrite that just to be clear. Now that we have a logarithm plus another logarithm with the same base, they're both common logs, they both have the same base 10. This is the log of x plus 1, common log of x plus 1, times 4x squared to the 1/2. Now I should simplify this. 4 to the 1/2 power is a 2. X squared to the 1/2 power is an x times x plus 1. So the common log of, just to be clear, I'm putting my brackets in. So the common log of 2x times x plus 1. And, depending on what you're wanting this to look like, you can distribute that in. So common log of 2x squared plus 2x. So that would be the fully condensed answer, written as a single logarithm. And you've seen us use this skill in terms of trying to solve. If you're in an equation, it's often important for your equations to end up being log of a single object equals something, either another constant or another logarithm or whatever. So being able to bring logarithms together is an important solving tool. And we'll see one of those at number 12. So this tool also expands, like this one does, to other disciplines, but this skill of contracting was much more useful for us immediately in this course. This expansion tool will be more useful as you go along in your studies. Okay, solving equations. So number 11 here is, it's a classic. You almost always see these on your tests. 3 to the 2x equals 7x plus 2. Now, if the variables weren't here, or if these were the same bases, this would be a much easier problem. But the bases are different, you have variables on both sides, so you've really got a lot of mess here. So one of the nice things about exponents is we have a tool that will pull any exponent down from any base. Logarithms, specifically this power property, allow us to take any exponent and pull it down. So all we need is a logarithm here. Now if they were both base 3, we'd use a log base 3 and it would destroy the 3's. If they were both 7's, we could use a log base 7 and it would destroy them. But when they don't agree, we can just use a generic log, and the natural log ends up being a nice generic log, often because we end up with a lot of e's later on, so getting used to using the natural log is handy. So you could technically use any log you want, but common log and natural log are our standards, so I'm going to use natural log here. So taking the natural log of both sides, Some people don't like that because you're bringing in this big natural log tool. But that natural log tool allows us to take our exponents and pull them down. 2x times the natural log of 3 and x plus 2, careful about these parentheses, times the natural log of 7. So it turned that exponential into a multiplication, and multiplication is something that we can handle a lot easier. So the purpose of putting in the natural log was to get those exponents down as multiples so we could handle them. Now the important thing about solving these, is just to remember that the natural log of 3 and the natural log of 7 are just numbers. If you had, like say, a 13, 29 there, you would just take that number and distribute it. So don't change what you're going to do. We tend to write them backwards, but it's the same. Like this was I think I said 29. You would distribute the 29. So I'm going to distribute the natural log of 7. So x times the natural log of 7 plus 2 times the natural log of 7. Now I've got x's on both sides. Usually when we're solving and we have x's on both sides, we try to get them on the same side. So in keeping with that, I'm going to subtract the natural log of 7 from both sides. You get 2x natural log of 3 minus x natural log of 7 equals 2 natural log of 7. Now this is where people often get stuck. They're not sure what to do with this. But I want you to think about what would you do if you had 7x minus 5x equaled, I'm making these numbers up, say 13. Well, you would look at the 7x minus 5x and say, hey, that's 2x equals 13, and then you could divide out that 2. Well, I like to focus on why do we do this? Why is it okay? You might say because these are like terms, but so what? Why does like terms allow us to do this? Or better yet, what's actually happening when we do 7x minus 5x? Well, what you're doing is you're taking the 7 and subtracting the 5, and then leaving that as the new coefficient of x. The reason that's possible is because what you're actually doing is factoring out that x. There's an x in both terms, and you're factoring it out to there, and leaving the 7 minus 5, which you can perform, giving you the 2. Every time you collect like terms, you're really factoring out the common factor of your variable. We just don't think of it that way. It's defined that way. This is how, what do? You subtract the 2 coefficients and you leave that as the multiple of x. That's what you've been doing. Down here, we can't actually perform this subtraction in the normal way we'd like to for like terms, but we can still use the kind of definition of like terms. We have an x in both terms, so factor it out. I'm going to factor it that way for convenience. It leaves a 2 natural log of 3 minus a natural log of 7, which again, if they were numbers, we could just take that subtraction. But since they are not like term numbers, they are numbers, they're just weird numbers, we don't actually want to take this subtraction, but we can still, it is now just x times whatever this weird number is. So divide by that weird number, by the 2 natural log of 3 minus the natural log of 7. On both sides, of course. And x equals 2 natural log of 7 over 2 natural log of 3 minus natural log of 7. Now, if you want to manipulate that a little bit, you can. Be careful, make sure those manipulations are legal. But that's a perfectly reasonable, exact solution. It takes a little while to get used to this particular skill of factoring out like this. But this is going to happen more and more often as you deal with logarithms, as you deal with irrational numbers, like even square roots, as you deal with complex numbers. When you're going to have something where they're all numbers, but you can't actually simplify it nicely. And you will collect like terms by essentially factoring. The nice thing is that's what you've always done. The bad thing is you're not always aware that that's what you've always done. So we just want to become more aware of that. Okay, number 11. How's my time? Not bad. Okay, number 12. Number 12 I referred to earlier. So we have the natural log here of 2x plus 1 is equal to the natural log of 2x minus 5 plus the natural log of x minus 5. So we have a fair number of tools for logarithms. Excuse me. a fair number of tools for logarithms that work as long as we have the log, whatever base it is, so the natural log is fine, of one thing being equal to log with the same base of something else. As long as you have a single logarithm equal to another logarithm where the bases match, you can solve by simply setting the arguments equal to each other. It's called the one-to-one property. And I always like to illustrate people. I ask them if log base 5 of x is equal to log base 5 of 7, what had x better be? Well, x had better be 7. Those have to match. It's a one-to-one function. So that's all this is saying. No matter how complicated they are, if you have the log base b of m is equal to the log base b of n, m and n must be the same thing. But to do that, you have to have a single log equal to a single log. That's not what we have here. The fact that they're natural logs aren't a problem. The part that's a problem is we have a logarithm equal to the sum of two logs. So we can't just get rid of the logs. What we have to do is make sure we express this as a single logarithm. Well, if only we had some sort of tool to take the addition of two logs and turn it into one log. Well, luckily we do. That was these compression tools. The logarithm of the sum of two logarithms turns into the log of the product. That's one of our compression tools. So this side will turn into the natural log of 2x minus 5 times x minus 5. Now, as soon as we have the log of something equals the log of something else, we can take each of those arguments and set them equal to each other. Notice I'm not saying we cancel out the logs or drop the logs. I don't want you to think of it that way. If the two logarithms are equal, then we can pick up their arguments and set their arguments equal. It might seem like a subtle difference, but it's a much more accurate way to think about it. So we have 2x plus 1. We got to multiply this together. So what? 2x squared minus 10x minus 5x plus 25. So 2x plus 1 equals 2x squared. I know you guys can do this part, but just to be super clear here, minus 1. So 0 equals 2x squared minus 17x plus 24. So we've got it down to a quadratic that's set equal to 0. So factor it if possible. If not, quadratic formula. And I know you guys can do that part. The one thing to be careful of is if you get any of the solutions that you get, make sure you plug them back in and make sure they're defined. Because remember, the logarithm cannot act on something negative. So if you get a solution like positive 3 minus 5 is still negative. So it can't be a number that works in here. If you got an answer like negative 2 times negative 2 is negative 4 plus 1 is negative 3. So negative 2 won't work. So make sure whatever answers you get, you plug back in to make sure they're valid. But the important thing with this question is to make sure you're bringing these together into a single log before applying the one-to-one property. And again, try to stick with the language and the mental process of you need a log equal to a log so you can set the arguments equal to each other. The more that you conceptualize it in terms of canceling the logs, the more you'll want to cancel them out here instead of here. So the more precise you can be in this kind of problem, the better. And the solutions to this are on the online thing. But you guys can do this part. Just make sure you check those answers for the domain restrictions of the logarithms. Let's see. That's the chapter 5 stuff. Let me jump to another video. I'm almost at my 20 minutes.